Hi everyone, today we'll be looking at the statistics paper of the A-level of October 2021. In question 1, we need to state one disadvantage of using quota sampling compared with simple random sampling. Well, we know that quota sampling is one of the two methods of sampling that are non-random. So quota sampling is a non-random sampling method, and therefore it is prone to bias. So we need to refer to the keyword non-random because this is what's making it susceptible to bias. In a university, 8% of students are members of the university dance club. We take a random sample of 36 students, and we've got the random variable x representing those who are members of the dance club. Obviously, this is a binomial random variable. We've got 36 trials. The probability of success is 8%. We need to use a suitable model for x to find the probability of x is 4 and the probability of x being greater than or equal to 7. So I will start by stating the distribution that x follows. It's binomial with n 36 and p 0.08. So the probability of x is 4 is simplified with the calculator 0.1674, and the probability of x being greater than or equal to 7. In order for me to use the calculator, I need to turn it into a less than or equal to probability. So this is 1 minus the probability of x less than or equal to 6, which is 1 minus 0.97766 which turns out to be 0.0222. Now, only 40% of the university dance club members can dance the tango. Find the probability that the student is a member of the university dance club and can dance the tango. So we need to find 40% of 8%, which is the percentage of students who are members of the university dance club. So we simply need to do 0.40 times 0.08, and this gives an answer of 4 over 125. And then D, we've taken a random sample of 50 students. What is the probability that fewer than 3 of them are members of the university dance club and can dance the tango? So I will now need a second random variable to be defined, y, to be the number of students that are member of the dance club. So they have to be members of the dance club and also can dance the tango. So this is the new random variable we will be using. We have taken a random sample of size 50, which means my y follows binomial 50 with the probability of success being 4 over 125. We need to find the probability of y less than 3. It's a strict inequality. This means that it's the same as the probability of y less than or equal to 2, which my calculator gives me as 0.7851. In question 2, Mark took a random sample of 16 students from a school, and we have recorded the number of letters in their last name, that's X, and the number of letters Y in their first name. We have the scatter diagram shown here showing the results. So each of these crosses corresponds to one student, and it's the number of letters in their last name and their first name. So we are being asked for 1 mark to describe the correlation between X and Y. Well, we see that as we go to the right along the X, the Y tends to go down. So this is negative correlation. So this is all I'm expected to say, negative correlation. Part B, we have a suggestion by Mark that parents with long last names tend to give their children shorter first names, and we need to comment on Mark's suggestion by referring to the scatter diagram. Well, we simply have to say that as x increases, y decreases. Hence, Mark's suggestion is valid. In C, we need to use our calculator to find the product moment correlation coefficient for this data. So I simply plug in all the data on my calculator. I get R to be negative 0.5446. The fact that I got a negative answer is a good sign because it supports the idea here that we have qualitatively said that there is negative correlation. Finally, part D, we need to test whether or not there is evidence of a negative correlation between the number of letters in the last name and the number of letters in the first name. So we need to conduct a hypothesis test here. So I will start by writing out my hypothesis. So my null hypothesis H0 is that rho is 0. The population correlation is 0. The alternative is that rho is negative. I'm working at a 5% level of significance. We have found from the table of values a critical value which is minus 0.4259. So how do we find this value? We've got the table of critical values for correlation coefficients given here. We are working at the 5% level of significance, so along this column here. We know that the sample size is 16, so the 0.4259 is the critical value. It's the value that if I exceed, I will be able to reject the null hypothesis. Someone might be wondering, why did we say that the critical value is negative? Well, the critical value is negative because I'm looking for a negative correlation in my alternative hypothesis. I always find it useful to draw a bell-shaped curve here, and I will sketch what's happening. This is minus 0.4259. This here is the critical region. We have found a value of negative 0.5446, which is obviously within the critical region. So we say that the negative 0.5446 is less than negative 0.4259. So this is significant. We reject H0. And the only thing missing is a qualitative conclusion. So there is evidence of a negative correlation between the number of letters in the last name and the number of letters in the first name. So we always need a conclusion in context, otherwise we won't get full marks, which pretty much uses the words, the keywords arising from the question itself. Question 3, we've got staff who is studying the large dataset for September 2015. He has coded the variable daily mean pressure using this formula here. He's got data for all 30 days from Hearn. And we've got the sum to be 214 and the sum of the squares to be 5912. We need to state the units of the variable x. We know that the pressure is measured in hectopascals. So that's the unit of measure for this variable, hectopascals or HPA. B, we need to find the daily mean pressure for these 30 days. I will start by finding the coded mean, y bar, which is sum of y over n, which is 214 over 30, which is 107 over 15. I need to decode this, go back to the original variable. So we know that y bar is x bar minus 1010. Just as a reminder here, when we've got the mean, when we've got the variable coded, then the mean gets affected in exactly the same way. So I replace y bar with 107 over 15 is x bar minus 1010. And this means that x bar turns out to be 1017. In C, we need to find the standard deviation of daily mean pressure for these 30 days. So what we need to do here is start by calculating the standard deviation for the coded variable y. So sigma y is the sum of y squared over n minus the sum of y over n all square root. So I will replace 5912 over 30 minus 214 over 30 all square rooted. This is giving me an answer of 12.09. We know that the standard deviation is not affected by adding or subtracting constants, so the standard deviation of y is equal to the standard deviation of x, and therefore the standard deviation of the daily mean pressure is 12.09 hectopascals. Now in D, we've got lots of information given here. Let's quickly go through this. We know that in the UK, when we've got a region of high pressure, we've got winds circulating in a clockwise direction. When we've got a region of low pressure, then the winds are moving in an anti-clockwise direction. We've got the daily mean pressure for a specific day in September of 2015 for Heathrow, Herne and Leuchars, and the cardinal wind direction here is given in random order: west, northeast and east, and we are assuming that all three locations are under a single region of pressure. Using our knowledge of the large data set, we need to place each of these wind directions in the correct location, and we need to give a reason for our answer. So we should have a good idea of where each of these locations is on a map of the UK. So I will actually draw a map of the UK. I will place the three locations and we'll try to explain exactly what's happening here. So this is the map of the UK. These are the locations for which the large data set is giving us information. Let's look at what kind of information will be provided up to now. We know that in Heathrow it was 1029 on this day, the mean pressure, 1029. In Herne it was 1028. In Leuchars it was 1028. This was a particular day in September, and we have already found from part B that the average for September was 1017 for Herne. So 1017 is certainly less than these values here. So we are looking at a system of high pressure. So it means that the direction of the wind is clockwise. So we can see what's happening here by drawing a circle through the three locations. I've drawn a circle here. It's going through Leuchars, it's going through Heathrow, it's going through Herne, and we've got winds moving in a clockwise direction because on this particular day we've got higher pressure than what we would expect based on the mean we have found for September for Herne. So if you look at Leuchars and if you take into account where north, south, east and west is, you can see that the wind is coming this way here. So it's coming from the west. For Heathrow, it's coming northeast like this. And for Herne, it's coming like this, which is east. So going back to the table, I would say that the Heathrow is northeast, Herne is east, and Leuchars is west. So we need to write down the direction, the wind directions, and we take into account the relative position of each of these locations on the map, as well as the fact that on this particular day, these values indicate a region of high pressure. In question 4, we've got a large college. It's producing 3 magazines. So we've got 3 events, G, E, and S, and this is the Venn diagram showing the different probabilities. We need to find the proportion of students in the college who read exactly one of these magazines. So this is simply the sum of 0.08, 0.09, and 0.36, because it's the only G, the only E, and the only S that we're looking for. So part A, we will simply add the 3 numbers, and we get that 0.08 plus 0.09 plus 0.36 is 0.53. Now, no student reads all 3 magazines, and the probability of G is 0.25. So we've got 2 pieces of information. There is nothing in the intersection, so this here is 0, and then all of G, all of these is 0.25. So I will start by stating that P is 0, and then I will say that the sum of the probabilities in G, so 0.08 and 0.05 plus 0, the value of P, plus Q is equal to 0.25, which means that 0.13 plus Q is 0.25, and therefore Q is 0.12. Now in C, it says, given that the probability of S given E is 5/12, we need to find the value of R and then the value of T. So this is conditional probability. It is certain that we are in E, so we are surely somewhere here, either here or 0.09 or R or P, and we are wondering on what is the probability that we are in S, so we could be here or here. So I could write down an equation in R and P based on that. So we have already established that P is 0, so the numerator is what I have ticked over what I have shaded in blue, which is R plus 0.09 plus 0.05 is equal to 5/12. This means that R over R plus 0.14 is 5/12. I will cross multiply to get that 12R is 5R plus 0.7, and therefore 7R is 0.7, which means that R is 0.1. So I will go back to my diagram now. I will update R with the value of 0.1. And the only piece of information I haven't used is that the sum of all of these probabilities should be 1. And this will help me find the value of T. We already know that Q, which we have found before, is 0.12. I might as well put that here. So it is clear now that the only unknown is the T, which is outside. So we can simply write down all the values and add them up. So we've got that 0.08 plus 0.05 plus 0 plus 0.12 plus 0.36 plus 0.1 plus 0.09 plus T is 1. So 0.8 plus T is 1, which means that T is 0.2. And finally, part D, we need to determine whether or not the events S intersection E dash and G are independent. Well, S intersection E dash means that I'm in S but not in E, so I'm here. And the probability of G, we know it's 0.25. I'll have to compare the product of the two probabilities with the probability of the intersection to see whether they are independent or not. So I start by stating that the probability of S intersection E dash is simply 0.12 plus 0.36, which is 0.48. The probability of G has been given to be 0.25. The probability of S intersection E dash intersection G means I'm in S, I'm in G, but I'm not in E, which is simply 0.12. This is 0.48 times 0.25, which is the probability of S intersection E dash times the probability of G. And therefore, since the two match, we can conclude that S intersection E dash and G are independent. We need to explicitly compare the product of the two probabilities with the probability of the intersection, and if they happen to be the same, then I can conclude that we are independent. In question 5, it's the heights of females from a country which is normally distributed. The mean is 166.5 and the standard deviation is 6.1. We are being given that 1% of females are shorter than K, and we need to find the value of K for 2 marks. I will start by defining X, my random variable, to be the height. We know that it is normally distributed with parameter mu being 166.5 and sigma being 6.1. We have been told that the probability of X less than K is 0.01. I can use the inverse normal function on my calculator to get that K is 152.3. B, we need to find the proportion of females with heights between 150 and 175 centimeters. So I simply have to evaluate the probability that I'm between 150 and 175. On the calculator, the normal CD option gives me 0.9148. Now, a female from this country is chosen at random from those with heights between 150 and 175 centimeters. I need to find the probability that her height is more than 160 centimeters. Now, this is conditional probability. I always suggest that you draw a diagram just to illustrate on what's happening. So let's do that. So I have drawn here my bell-shaped curve. It is centered at 166.5. We know for sure that this individual has a height between 150 and 175. So I'm certainly within this region here. And I'm wondering what's the probability I'm more than 160. So what's the probability I'm here? So I will simply do the probability of 160 to 175 divided by the probability I'm between 150 and 175. So this is 0.7749 over 0.9148 which gives an answer of 0.8471. In D, we've got heights from a different country normally distributed with a standard deviation of 7.4. We've got Mia, who believes that the mean height is less than 166.5, and she takes a random sample of 50 females, and she found a sample mean of 164.6, and the question is whether her belief is supported based on this data. So we need to conduct a hypothesis test. We start by stating our null, which is that the mu is 166.5. My alternative hypothesis is that mu is less than 166.5, and this is at the 5% level of significance. Now we have a sample of size 50. We have obtained a sample mean of 164.6, and the standard deviation is known to be 7.4. Under H0, which means that if the null hypothesis is true, the random variable x bar follows a normal distribution with mean 166.5 and variance 7.4 squared over 50. The probability of x bar being less than 164.6, so we inherit the direction from the alternative hypothesis, and we always use the sample mean we have found. This gives a probability of 0.03472, which is less than 0.05, and we say this is significant. We reject H0. So what has happened here is that we have observed something which is more extreme than the threshold dictated by the significance level. This means that we can conclude that there is evidence to support Mias's belief. In question 6, it's the discrete random variable x. It has this probability distribution. It can take values a, b, and c with these associated probabilities. We have been told that a, b, c are distinct integers in ascending order, and all the probabilities are greater than 0. We need to find the value of a, b, and c, and we need to show they're working clearly. So I will start by stating the obvious, that the sum of the three probabilities must be 1. So log a base 36 plus log b base 36 plus log c base 36 is 1. I use the product rule of logarithms, which says that this can be written as log of a, b, c base 36, which is 1. So a, b, c is 36. In addition, the fact that we've got a less than b less than c, and knowing that log of 1 base 36 is 0, and none of the probabilities is 0, they are all greater than 0, this means that a must be greater than 1, and so is b and c. Now I need to think of a decomposition of 36 into 3 integers, all of which are greater than 1, and none of them is equal to the others. So I can easily come up with the solution that 36 is 2 times 3 times 6. So again, 3 distinct integers, all of them greater than 1, all of them different, which means that a must be 2, b must be 3, and c must be 6. And then part B, we've got the independent random variables x1 and x2 having the same distribution as x, and we need to find the probability of x1 being equal to x2. In other words, think of this as conducting an experiment. There are 3 possible outcomes, A, B, and C, which we have found, by the way, to be 2, 3, and 6. And we want to find ourselves getting the same result in both times. So either 2, 2, or 3, 3, or 6, 6. So the probability of x1 being equal to x2 is the probability we get 2 both times, or we get 3 both times, or we get 6 both times. So this is log of 2 base 36 squared plus log of 3 base 36 squared plus log of 6 base 36 squared. I can multiply the probabilities here. It's log of 2 base 36 times log of 2 base 36, because the 2 observations are independent, so I can multiply out the probabilities. I put everything on the calculator and get an answer of 0.3814.